All right, so uh, the title of this talk is Foundational Models for Robotics, and especially how we can remove the engineer from the loop. But when it comes to this specific class, I think there are a few things that will be relevant for you. I know that the theme of the class is self-supervised learning. So here I'm going to talk about a few things. I'm going to talk about how we can try to use these self-supervised models, as Daniel said, for robotics applications. That's going to be kind of the first third of this lecture. Then I'm going to talk about how we can kind of use features from both vision and language models towards other types of robotics works. And then the last part, kind of the last segment, is how we can try to train our own self-supervised models for robotic systems. So I think there might be different topics that will probably be very relevant for this class. So I'm showing you a GIF over here. I don't know how well this is playing over the broadcast, but so these are some examples of things that we can do using these models for robotic systems. So this GIF is from a paper. We haven't published this paper in a conference yet. We kind of scrambled. Like we took 4 weeks to do this paper. It was actually the fastest paper I've ever done in my life. It was called ChatGPT for Robotics, and we were basically investigating. I know this is kind of the hype right now. Every single day on Twitter, on LinkedIn, we just see people posting about large models, and what we thought was, let's try to investigate if we can use these large models for robotic systems. So we investigated how we can try to remove the kind of the technical person from the loop and just try to have a user control robots in natural language. So you just tell the robot to inspect the shelves, and it generates the code that inspects something. Find where I can warm up my lunch, and it finds a microwave, or build a Microsoft logo, and that it basically builds that logo from scratch. So this is very different from how robotics has been traditionally done, and I have been there on the kind of the traditional robotics space, and I find this line of work very exciting. But yeah, let's get to the details. Before I speak about the technical work, I just very briefly want to say kind of a brief background about myself. I am working at Microsoft right now as a researcher. I did my PhD in robotics at CMU, and throughout my PhD, I've done a few internships, which is something that I highly recommend. Whether even if you want to go to academia after your, let's say if you're in a master's and want to go to PhD, or if you're in a PhD and want to go to academia or industry, I highly recommend doing a few internships to kind of get to know different groups and different environments doing your graduate studies. So today, I'm mostly going to focus on works that are related to this multimodal robot control using vision and language models, and I'll talk about generative AI for decision making. But throughout my PhD and past experiences, I've done works on many other topics. A lot of my PhD thesis was on this topic of autonomous drone cinematography, so filming moving targets using drones. So it was a big mix of learning kind of artistic objective functions, machine learning for human-computer interfaces, and actually field robotics and robotics deployment in real life. Kind of along these lines, I also did a lot of work on emotional camera control or emotional human-robot interfaces. So you can control robots and try to express different emotions while you're filming. You're making movies autonomously using robot cameras. So this was a pretty different topic than things we normally see in the computer science space. And I also had some work on learning visual motor representations for robot control. I'm not going to talk about this three bottom works, but I'll mostly be focusing on the top two today. But if you have questions later, I'm happy to answer that as well. All right, so I don't have to be the one breaking the news, especially to this class, but large models are really revolutionizing generative AI and many topics that we've been seeing lately. You have seen, of course, this happening with text generation, with conversational models like ChatGPT, image generation, and even a few other topics that we've been reading about lately. I just put a few examples, like text to video, text to 3D models, image editing, and many other types of problems. But one aspect that people are just starting to realize is that besides this kind of one-shot applications where you go from text to an image, text to a video, we should also think about generative AI revolutionizing decision making. And by decision making, maybe I should have worded this as long-term decision making, or taking those many steps towards accomplishing your objectives. Which, for example, that paper of the ChatGPT for robotics. Now, if you have some high-level objective, maybe it's not decomposable into a single output, but maybe like if you want to warm up your lunch, like this, there are multiple things that have to happen kind of in sequence for you to accomplish your objective. It's not a kind of zero-shot generation. And maybe a video that I really like is from this company called Adapt AI. They released this video actually a few months ago from one of their models where the user interacts with the bot saying, I want to find a house in Houston that can fit a family of 4 under some budget. And the model is able to call a bunch of APIs and kind of buttons on a website to accomplish that objective. So it's not a kind of zero-shot generation, but it involves multiple steps of reasoning to accomplish that objective. So there's just 2 examples. Now, the first one was kind of physical. The second one is purely virtual. But I see this as the next. Maybe if you want to be one step ahead of the hype, I think that's probably where I would be looking. And that's where my own research at Microsoft concentrates itself. So the kind of the high level goal of my work has been to use these large models to empower users with the full capabilities of generative AI. So we're basically modeling this, this interface between the human user, hopefully a non-technical user, and these systems that make decisions over multiple time steps. This can be purely virtual systems, like calling functions on a computer. This can be robots, so we're calling APIs that move electrical motors, actuators, or sometimes we can even abstract this and kind of have the interface between the human and another model. And the types of challenges that I'm going to be focusing on today are challenges pertaining to this human model interaction, challenges related to how to incorporate multiple modalities of data into your context. So as let's say the input to these large transformers, these large models. This can be text, image modalities, actions. Oftentimes in robotics, we have depth images, LiDAR point clouds, many other types of modalities or infrared cameras, things that we don't normally talk about in traditional computer science. And also we would love if these models could generalize for multiple tasks as opposed to being specific to a single task. But I think many of these models we've seen today are quite general in its nature, so that's a good thing. So the kind of the outline of this talk is I'll be kind of separating these 3 challenges. I'll kind of describe in detail one paper related to each one of these main challenges. First, I'll be talking about the ChatGPT for robotics paper. So it's very much into how we can close the loop between the human user and the model itself. So one thing that we have today, and I know I'm focusing here on robotics, but you can generalize this to many other types of human-computer interfaces, is that we usually have an engineer in the loop. And by that, I mean, we have a human who is usually a technical human who has a objective function in their brain. So you want to do something, and then you write code that is specific to doing that task, and then you deploy this. I know I have a robot here, so like you could deploy this on a robot, things maybe work or don't work, and take feedback from this deployment to improve the code, really given your objective function, improve the code, and you kind of do this loop sequentially until the behavior converges to something you enjoy. But what these large models allow us to do is to change things slightly. So instead of having an engineer in the loop, hopefully we want to have a user, hopefully a non-technical user on the loop. So you're not directly, in the code writing process, but you express your objective functions as a simple prompt or an objective function. Right now, I think through text, but in the future, maybe through other types of interfaces. And the model itself is the agent that writes the code, and hopefully in the future also looks at feedback from the code and improves this, or maybe you as the human supervise this loop on a higher level, and you keep interacting with the model. In the case of this paper that we published, the idea was to investigate how we can have this more natural interfaces or have a common set of principles that can be used to accomplish any robotics task. So we investigated many tasks with drone inspection, with manipulation and embodied agents, which is something very, very far from the traditional robotic space where people do a whole paper, a whole method that is specific to one application and even one robot, and maybe even a specific task with a single robot for a single type of application class. In this paper, we try to be as general as possible and say, if we were to do a very generic interface using ChatGPT, like how can we make this happen for any type of context for robotics? To make things a little less abstract, let me show you a video of how this looks. So this is a ChatGPT controlling a real life drone. Let me skip to, yeah. So we basically have this ChatGPT interface, and let me just pause for a second. Actually, something funny here was at the time we published this paper, we saw that if we didn't act quick enough, somebody else would do this paper. So this was kind of there are a few moments where you clearly see a kind of a low hanging fruit, like paper wise when you're in the academic world, and we saw that clearly, like this is a really cool technology. Somebody's going to use this for something, so we have to be the first. So instead of waiting for a ChatGPT API or something like to be released later, we just literally used the browser version of ChatGPT. So the entire paper was done using the browser version before any of the APIs came out. It's some of the hacks you do as a researcher sometimes if you want to get things done quickly. But yeah, so going back to the video, we have this interface, and I'll talk about the prompt a little later in the talk. So I know I skipped the prompting aspect here, but basically, we have this interface where I just tell the drone, I'm thirsty. Can you find me a drink? And this ChatGPT interface allows us to very naturally communicate with the robot. So it even asks, there are multiple options of drinks in the scene. There's a coconut water. There's a can of Diet Coke. Is there anything in particular you want? And I say, I'm looking for something healthy. And then it produces code that goes towards the coconut water, which is supposedly the healthiest option in the scene. Now, if you're familiar, maybe if you come from the natural language processing world, this looks fine. But if you're coming from the robotic space, this is very different from how things have traditionally been done. Usually, like things are very hacky. They're very specific to a single robot, to a single task, as opposed to being a natural conversation. Yeah, and then we call the appropriate APIs with the robot and go towards the coconut water. And then we keep going. So we say, I'm still thirsty. Can you find me something with sugar and a red logo? And the model automatically detects that, oh, there's a can of regular Coke in the scene. So that's probably what you're referring to, and calls the appropriate APIs for the robot control.
Oh, can I ask a question?
Yeah.
Sorry, Adam, do you want to?
No, go ahead.
So in your prompt, did you specify what are the set of objects that you have in your space and your room?
Yes. I'll give it the yeah. So in this case of the drone, I said, oh, I have these types of objects in these positions, but I listed every single object that existed in the room.
Got it.
I'll give some examples later where you don't specify, like the case of the GIF earlier where you say, warm up by lunch. We didn't specify which objects existed nor where they were. So the robot used the APIs to produce code that would find the appropriate objects. But I'll mention later like how to design your prompt for each application of robotics.
Got it. Thank you.
I had a quick question about the control piece of this. So are you assuming that the robotic platform, you've kind of offloaded sort of the more conventional like navigation, tasking, and things of that nature, and so you're kind of translating from natural language to sort of a higher level objective, like go to drink, and then you assume, right, that the robotic navigation system will handle the execution?
Yes, that's correct. And I'll on the next slide, I think things will be more clear on what are the assumptions I make on those design principles. So yeah, I'll defer this question for the next slide. It'll be very clear which assumptions I make and which high. But yeah, the principle is we're calling high level APIs that we know can be executed. Yeah.
Okay.
And then the last thing I wanted to show. Yeah, actually, this one was funny. Like on this one, we say, take a selfie using a reflective surface. And one of the objects in the scene was a mirror. So it was interesting that the ChatGPT produced the code to both go towards the mirror and then move the angle of the robot to look at the mirror while going there. So the drone took a selfie. And then some tabloids like picked it up and said, "Oh, drones are taking selfies." And it's funny how like a lot of journalists really twist what's happening in papers. Yeah, and this one was the last one I wanted to emphasize just on this drone video. The activities I showed before were quite simple, just go to a position. But on this one, I said, I have a shelf and I might be missing some packages. Can you inspect the shelf? I give it the dimensions. And then I want to do a lawnmower pattern. So it's kind of a zigzag behavior on each shelf. And, this might take, it's not a super complicated behavior if you're coding this out, but it's a little annoying. It might take you, some tries and maybe 15 minutes if you're coding this to a robot, 15 minutes, half an hour if you're testing this. And ChatGPT was able to deploy and do this while loop and kind of do height increments and come back to the original position, and it even explains what's happening. And yeah, we're quite surprised by how capable these models were for robotics. Yeah, and then you can see it inspecting the shelf. But yeah, going to, a lot of you are wondering, how are we doing this in practice? So in the paper, we have a series of design principles and kind of assumptions that we make to guide us on how we can interact with these models. Things might change because these models are constantly changing, but I think this is a set of basic design principles that most people should be using, even as these models get more capable in the future. So the first step is we define a task-relevant robot API library. So for whatever task you're doing, you're going to write a bunch of functions that can be executed for your application. For example, we have this example case of you want a robot to cook a omelet and serve it to somebody. So you might have a bunch of APIs that are locate object or move to location, cook an item, grab an object. This can be as low level or as high level as you want. It doesn't matter if these are APIs that come from classical controls. I don't know, could be a PID loop that has nothing learned. This could be a object detection network, like a YOLO network running to detect objects in the scene. This could be like whatever function that you can execute to with a high degree of certainty. Then after we define the function that we can actually call for the robot, then we build the prompt itself. So in the paper, we show many different types of ways in which we can prompt the robot. We found that by using something like telling ChatGPT that, oh, consider you are a home assistant robot. Your goal is to prepare an omelet for an elderly person, and you are equipped with the following functions. And then we kind of list, almost like a kind of Python docstring. We list every function that exists, and we give the documentation of every function. So we say, no, these are the inputs, these are the outputs, this is what this function does. But by naming the functions with very clear names, like I could just call this F1, like function 1. But if you name the function with a obvious name, as a human readable name, this is better because you're dealing with a language model. So if it's a very obvious name, then it's easier for the model to call this, as opposed to only relying on the on the documentation. And then we say output Python code that achieves your objective. We show a few different types of ways of prompting. We also tried with using some XML tags in the prompt, a few other things, but roughly this type of prompting that I'm showing here works really well for robotics. Then the third step is, with the user on the loop, you kind of iterate on the solution quality and safety. In the examples we saw with the drone, this is kind of a one-shot generation. They were simple enough that whatever code ChatGPT outputted could just be run and everything was fine. But I'll show a couple cases later where we actually required a conversation with the model. And the reason why we used ChatGPT as opposed to just GPT-3 was the ability to chat with the model is much easier for the user for corrections than if you have to kind of regenerate than if you have to kind of do everything from scratch again as your interaction loop. Because you can just say that if there's like something slightly off, you can just say, like for example, in the shelf inspection problem, there was a case once where it was inspecting the shelf like well, but everything was shifted. So I just told the model, instead of like going back from the original prompt and kind of trying to re-say things on the prompt, I just said, oh, like everything is almost correct, but you have to shift your positioning by half the length of the shelf. I just said this like as a next iteration, and then it produced the new code with the correction without me having to redo everything from scratch. So that's very useful. And then like once you're happy with the solution, hopefully you have a simulator where you can kind of test the solution quality, then you execute this on a robot. Yeah, so I said before, like sometimes it's not enough or the task is too complex that you cannot have a kind of a zero shot output from the model working properly. So you need the conversation. So in this case, we had a manipulator, and I'll skip a little in the video. So initially, we're doing very simple tasks like throw the blue block in the green bin, and the robot basically picks it up and puts it there. It's able to use all the functions we defined in that low-level API library. We had functions like turn on your suction cup or go to position, like things that are very, very simple. And we do a few trials here. Yeah, basically put something on the mat. But later we want to do something that is much more complex. Like on the last example, we're trying to build the Microsoft logo, like using the blocks. And if you think about it, like building the Microsoft logo involves like many steps. It also involves the idea of knowing how to arrange the colors together. In this case, I guess in this specific prompt, we were telling it how to arrange the colors, the color configuration. We also had some tests where we just said build the Microsoft logo using the blocks without telling it like the model itself had to know how the Microsoft colors are configured in the logo. But the issue here is to output Python code that uses the very low-level functions was very complex because there were a lot of steps by using those low-level functions. So we learned that by using some sort of curriculum learning approach. So we first had to ask ChatGPT to create a higher-level function of pick and place a colored block somewhere, and then it used that function that it itself generated using the low-level functions to build the Microsoft logo. But we saw that this kind of intermediate step, using the human to direct the model to build a intermediate level function, was very important if the task is too complex. So that's something to consider if you try to do something very hard. Yeah, then it's building the logo. A few other interesting things are.
Sorry, can I ask a question?
Yeah, go ahead.
So in the case of building Microsoft logo, I guess the robot knew what colors, what blocks of what colors you have, where they were, and I suppose also in the prompt. So basically, all that the prompt needed to generate is what block to pick, and where to put them, right? So like kind of source and destination locations.
Yeah, in the case of the logo, I don't think we had the positions of the blocks hard coded. I think I had this external camera, and I think we're running a network for, well, we had a network that was detecting the positions of the blocks. Well, yeah, but the detection was not done by the language model itself. It was kind of given by another model. Yeah, but we can either hard code this, or the position can come from some other model that is running on the robot. But yeah, the task was, I guess the difficulty was coming from how to call the right functions in the right order for the robot.
Right. If you just told the robots or ChatGPT that you know well I suppose ChatGPT at that point had the camera that well okay, so actually maybe this is not quite right, but then I guess let's say you have a GPT-4 that can see things as well. If you just told it that like build Microsoft logos, would you expect it to just generate all the sequence of commands with basically just minimal information given?
Yeah, I think the game changes with GPT-4. And actually, I haven't been, so I think in the public APIs, you cannot use the image input functionality as of now. And even in my team at Microsoft, I think nobody yet has had access to the image functionality for GPT-4. But that changes the game because, like, for example, I could pass, if I was using both the image and text modality of GPT-4, maybe I could pass an image of like the actual logo, let's say an image of the logo, and say, build this image using your robot functions.
Got it.
That would be a way.
Yeah.
Yeah. And also related to how to find the objects, like I think this was a good one. Like in this case, we had this other set of tasks using a embodied agent, where we were saying, find and navigate to a bottle. So in this case, we didn't hard code any object position, but we told the model that it had access to a function that would like get bounding boxes out of every object that exists in the word. And ChatGPT basically built a perception action loop. So there's a while loop that says, while I don't find the bottle in my visual detection system, I'm going to call this function to explore. So it basically turns around or moves to a random location. And then whenever it finds a bottle within the detection, I think we're using the YOLO detector, then it will navigate towards that position in space. So it doesn't see any bottle, so it just explores and turns around. But then at some point it does see a bottle, so it goes towards the bottle. Or the same thing with couch. And yeah, even have kind of high level concepts. Like we're not saying go to the microwave. We're just saying I want to warm up my lunch. Then it's able to, like, out of all the objects that it sees, it's able to call it goes towards the object that makes the most sense for the sentence you have as the input. We also tried a few experiments.
Question.
Yeah.
So, like, obviously, especially when you're combining multiple models together, like I think you mentioned that YOLO was being used for object detection. I would expect that like any error in any part of the calculations is really going to become quite catastrophic in terms of getting to your final result. Do you see any kind of like error correction behavior in ChatGPT, or does that just kind of compromise the whole system?
Yeah, it's a good question. I think the important thing is, let's see if we have the actual code here. Okay, so yeah, this is good. The important thing here is, like, just like in traditional robotics, you have a feedback loop. So even if your calculation is like, even forget about ChatGPT, like if you just were programming if you had a little robot that you're programming to go to the bottle and you're doing everything yourself, you do a while loop where you would basically take a small, like you find the segmentation of the bottle, and then you take a step towards this, like a small step towards this bottle, and then you recalculate everything from scratch. Like, so you keep doing, keep taking small steps, and at each single step you recalculate the object detection. So this way, even if you have a small error into the bottle position in the very first frame that you capture, you will, like, if your error is not too big, then you're going to self-correct, and then you eventually go towards the right position. So as long as ChatGPT is able to create a feedback loop or code that emulates a feedback loop, then you're okay. Like you're going to correct for errors. So that's how I would like try to correct for errors.
Okay.
The last experiment I had was this. This is quite hacky. I think with GPT-4, you can even ignore this experiment we did, but we tried even describing the word, kind of describing an image to the language model in terms of like centroids of, like we ran a segmentation network on the image, and then we got all the centroids of the objects, and we just described that in a textual format, like saying chair 4 meters away at a 25-degree angle to your left. And we do this for every single object in the scene. And then we tell the model, navigate towards the chair or whatever. And we keep passing, and you take a step, and then we keep passing textual descriptions to the model. It worked. It wasn't the best thing, but I think with GPT-4, you can get over these horrible hacks that we did for describing the image to a language model. And there are even some other interesting papers that kind of do this, that do this in much better ways. But we just wanted to not, we didn't want to have to retrain any networks. We were just using ChatGPT as it is. Yeah, so, and just to wrap up the segment on ChatGPT, we released a, so given that this like prompting models and especially in the robotics context, it's a very empirical science. There's no, nobody knows what the right way is. So we built a open source repo on GitHub, which has basically the proposal is to become a prompt library. So anybody can try things and post things that work well or don't work well, and kind of build a community knowledge over like how to prompt these models for robotics. We give like for every example we give in the paper, we kind of give the entire conversation, like the entire history of the conversation and some videos and GIFs. And we also provide a simulator where, if anybody wants to try this out on a robotic simulator, you can just download the executable file and kind of do your own thing with this repo. So I think we all have almost 1,000 stars on GitHub by now, and it's pretty cool. Like I'm not sure if we're like, I was expecting to see a few more people contributing to the prompts, but still, it's I think we have a few contributions there, and it's, I don't know, we're gonna try something new. All right, yeah. So I'll go quickly over the other two works. I think the first one was probably more interesting for the class, but I'll go over quickly over the next two works, and then we can leave space for questions.
That's great.
All right. So the second one that I was going to talk about is how to fuse multiple modalities of data within a large model. So for this specific work, we were trying to model. And by the way, all these three works were done in a. I'm showing the most recent one first. This was like, this paper was done before all this crazy GPT models were released. So now everything we have in this domain is like gets outdated really quickly. So maybe you'll see a few things in these slides and you'll say, oh, you can probably do this in a thousand different better ways. But I think the concepts here are still interesting for you. But okay, so in this paper, I was trying to model this interface between a human and a robot in terms of modifying trajectories. And there are many types of interfaces that you can use to control a robot, but natural language is by far the easiest one. That's how we communicate with each other, so that's more natural. To make things a little more concrete, we're trying to solve, like to work on scenarios like this, where a robot is doing something initially that is not optimal, and then you give a natural language command to the robot, like stay further away from the glasses, and the robot shapes its behavior to obey your language command. Yeah, we had some mathematical definitions, which if you're interested, you can take a look at the paper. But the main objective here, and this is where it's a little bit different from the, like, instead of purely using those kind of generative AI models here, I was both using pre-trained features from large models and training kind of my own layers on top of those pre-trained features. That should, like, so in this case in particular, I was using features from Distilbert to kind of capture the language commands from the user. So you're trying to stay away from the bottle, for example. I have clip features that are frozen pre-trained models from clip that find the similarity between my language command and the images of objects in the scene, because I'm trying to, because usually our commands refer to a specific object or to a set of objects in the environment. So that's why we do this cosine similarity calculation over here. And then what we did was we trained a few transformer layers on top of these features coming from the language commands, from the images of the environment, and of the geometrical data of the scene. So we assumed that we had some object detection network that would find the positions of every object in the environment, like on the tabletop or in the scene. And then we can output the modified trajectory for the robots, and then execute this using different inverse kinematics modules, either on a manipulator, on a drone, or whatever type of robot you have. A trick that we used was that, especially for robotics, we don't have a data set of corrections of robot trajectories, so we had to basically create our own. For those of you who are working with things that are maybe not exactly on a purely textual domain, you might have to use this sort of procedural data generation using some heuristics. We generated a bunch of kind of fake trajectories, fake word configurations, and we calculated kind of a corrections using a motion planner, with full knowledge of the environment, and to kind of fake the visual aspect of the scene, we had a web crawler that was just getting a bunch of images of each object class, kind of random images of each class to input into the clip embeddings. Yeah, so I'll just go quickly here. Yeah, so we're using the frozen embeddings, and basically, so and then we're able to deploy. So we use that procedural data, and then we deploy this on the robots to modify this trajectory. So you can say, reduce the speed if you're close to me, and then we have a modified trajectory in case you want to have knives on your robots. Or if you have a cup of tea and it's getting too close to your laptop, you can say keep a bigger distance from the computer, and it's going to execute that behavior. We had a bunch of other results in other robot types, so it doesn't have to be only manipulators. We had drones, so you go to the bottom, fly slow if you're close to the table. The drone is shaking in this image because we had a horrible controller in the simulator, but it wasn't supposed to be shaky. Or you can stay further away from somebody or someone in the scene. We had we had this spider robot as well in the simulator. Yeah, these are pretty toy settings, but just shows how this works. In the end, since we're dealing with something that is ultimately we want to make sure the human is happy with the results of the system. So in the end, oftentimes you do have to run user studies to make sure that whatever you're developing works well. So we compared our natural language interface with other types of interfaces like kinesthetic teaching, where you literally grab the robot and kind of show what you want to do. Parameter tuning, where you ask a user, sometimes a non-technical user, to play with a motion planner, which is oftentimes pretty hard to do. Trajectory drawing. Imagine you have an iPad in an industrial setting and you just draw whatever trajectory you want to execute next. And we compare these with different types of quantities, like is the user more satisfied? Is this easier to use? How many iterations does it take for the user to achieve their objective, success rate, the time of interaction, etc. For example, you can see that programming ends up being a lot more time consuming than just using the natural language interface on average. And we saw that using our natural language interface, it tends to be better in many of the metrics we're evaluating. I know I want to like finish this, so I'll just go over the kind of the last work, where if you think about training a model for multiple tasks, this was a attempt we made for training a kind of a GPT style model for robotics. So the same way that GPT for language is trained with predicting the next characters that we see in the training corpus, we thought, can we try to do a similar thing for a robot system? So we can have whatever inputs to the system, then we try to predict whatever the next output is going to be. So that the thought was, let's say if we have a self-driving car, and if we're predicting the next steering angle for the car very, very accurately, maybe you can get this kind of pre-trained transformer is going to have some notion of environment mapping, of motion planning, of prediction of other agents' behaviors in the environment. The same way that we can kind of obtain a lot of knowledge about semantics, about grammar within a GPT-style model. So instead of having a traditional autonomous systems pipeline where you have different blocks that are hand designed by an engineer and operating sequence, the thought was, if we make a foundational model for robotics, we can kind of use this common pre-trained representation and features towards multiple downstream tasks that are supposedly unrelated to each other. So the same way that a GPT model works, we predict we actually do a slight modification. Instead of only predicting the next words, here we have actions and states for the robot. So we kind of intercalate these over time, and we're always predicting the next actions or the next states in the data set as the pre-training for this work. And then we can fine-tune small task-specific networks on top of these pre-trained features for localization, for mapping, for safe navigation, for many other downstream tasks. I'm going to skip a few things. So these are the simulators we had. So I had this kind of very simple autonomous vehicle simulator operating in I basically scanned a few floors of my office building at Microsoft to collect semi-realistic data. We also have this habitat simulator, which is kind of home environments. It's based on 3D scans of houses. And the input here are images. Then we can train this pre-trained model that uses a lot of, just like a GPT model is able to output reasonable sequences of words, this pre-trained model for robotics outputs reasonable sequences of actions for the robot. So it's just kind of moving around without any specific goal in mind, but it's not crashing, it's just doing something safe, which represents the data distribution we saw in the training data set. And then we fine-tune this pre-trained model towards multiple tasks like mapping, navigation, localization, etc. Yeah, so this is the deployment, but I'll just skip this. We had some tests in real life as well, so we showed that this works with a real life robot car in my building. And yeah, so I'll keep this short. So I'll just, before we get to the questions, I really want to thank all my collaborators at Microsoft and other universities that helped in these papers. Of course, it's not a sole effort. And yeah, I would love to open up for discussions in these last minutes and hear any questions you have.